Welcome to part 3 of 16.2. So we're just going to finally complete this section. We're going to cover line integrals of vector fields, also known as work, today. So remember in chapter 12, we saw that if we have a constant force and a specified distance, then work could be calculated just using that work is the dot product of force and distance. Now, that doesn't work in most realistic scenarios because the force might not be consistent, it might be varying, and same with the distance. And so we have to look to see how do we handle calculating work when we have a force function that has variables in it. Like, how do we handle that? So we've covered vector fields and line integrals both separately, but now we're going to put the two together. We've got some pictures down here to give you an idea of like what that is. So in this first picture, it's 2D. We've got a vector field on our graph. And then this red line right here, I'll just emphasize it a bit. This red line here is a force vector that is moving through the vector field, okay? And then in 3D, although it's really painful to see it, we have another vector field and we have another force vector. The force vector could be many different things, and the field itself could be many different things. So we could think of the vector field as being a gravitational field, a magnetic field, airflow, or fluid flow. And then we just want to compute the work done by a force in moving a particle on some smooth curve within that field. Okay, so in each of these cases, this curve right here, that is the curve C. Okay, so we're going to try to move some particle along that curve. Same in the 3D case. This is our curve C. Okay. Now let's say that I guess I actually want to talk a little bit about this. Hold on. So we've got a 3D octant, and I'll go with 3D because the 2D is a much easier case to think about. Let's say that we've got some curve and it starts down here at P naught. And then it travels through space and it is going in a direction. I'll put my direction arrow on it. And at some point in time, we're going to get to some P sub I minus 1. And then at the next point in time, we'll be at some P sub I. So those are just 2 points in space. The distance between these points, we could call it a delta S. And then we could look at P sub I minus 1, and we could calculate a tangent vector, T. Remember that the unit tangent vector is r prime of t over the magnitude of r prime of t. And so we could think of this as like a velocity vector. And if we were to multiply a velocity vector by a distance, by a time, maybe some sort of dt, then we would be able to come up with a distance. Okay, so we got to figure out how that works. And then also in this picture, there's some sort of force vector that's moving in some direction to push a particle along the curve. Okay, so if we build our work integral without using Riemann sums or anything but if we build it, we have to look at it as we've got our force vector evaluated at our parametrization of the curve. And what that does is it fixes our force field on that curve so we can see what's happening there. So this is our force. And then we have our r prime of t over the magnitude of r prime of t. That's our unit tangent vector. And then we've got this ds, which is change in length. Okay, so we have this ds here. Now, if I was to write out what ds is, it is the magnitude of r prime of t dt. And then, so now what we've got here is the unit tangent vector times r prime of t, the magnitude of r prime of t, times dt. So then those magnitudes of r prime of t, those are going to cancel out. And we have this final form right here where we've got just velocity times time. dt is just a small change in time. R prime of t is velocity. And if you take a velocity and multiply it by the time, as long as the units are the same, you get a distance. So we really are looking at force times distance, except because we're dealing with vectors, it's really a force dotted with a distance, which we know from before in chapter 12, that's just work. Except we're calculating like an infinite number of these little products, and then we're adding them up infinitely, and that's what gives us our integral. So work is going to be the integral over a curve of f dot dr. And we just have to remember that the way this is written is an integral from a to b of f evaluated at the parametrization dotted with r prime of t dt. Okay? If we can remember those, then we can see very easily what it is that we need to find. So if you're asked to calculate work, or to calculate a line integral of a vector field, then looking at that second representation, I can see I need r of t, so I need a parametrization of my curve C. I need r prime of t. I need to evaluate my vector field at r of t, and then I need the dot product of those two. Okay? Now, before we get to some examples, what I want to do is let's see how we can make our line integral of a vector field look like something we have already done. So in this first representation here, I've got the line integral over C of f dot dr. If I write out f with its components p, q, and r, that's going to be this right here. So all I've done is written f in component form, and then dr, remember, is r prime of t dt. So here's it in component form. Okay, so this is f, and this is r prime. Okay, now if I go ahead and do that product, that dot product, then remember a dot product gives you a scalar function. So what we're going to do is multiply like components and then add them all together. So this is where I get px prime plus qy prime plus rz prime, and then there's the dt at the end. If I distribute that dt to each one of these, what I have to make note of is that I have an x prime dt, I have a y prime dt, I have a z prime dt. Well, we know from before that x prime dt is just dx, y prime dt is just dy, and z prime dt is just dz. So then we can rewrite our integral, or now what we have is a sum of three integrals, as the integral over c of p dx plus the integral over c of q dy plus the integral over c of r dz. And then we can rewrite that and look at this form. This is what we were just doing in the previous video. So line integral over c of p dx plus q dy plus r dz. So it turns out that we get this great equality right here. And that means that, well, when we are calculating a line integral of p dx plus q dy plus r dz, we're calculating work. If we've got a force vector and a distance vector, then this is work. That's just one application. I do want to stress that when you calculate a line integral of a vector field, it's not necessarily work, but it can be. And so just like we like to have an application to think about when we're dealing with a single integral, we think of area under the curve. A double integral is volume under the curve. A triple integral is something in fourth dimension. We like to also be able to think of there being some application for a line integral of f dot dr, and it could be work. All right, so all these forms are equivalent, and that's the part that you have to get comfortable with. Like, different scenarios are going to lend themselves to using one form or the other, and that's the comfort level you've got to get. So there are a few important ideas that are mentioned all throughout the section and the exercises that I've tried to summarize right here. The first one, The work done by a force field to move a particle along a curve will be negative if the field impedes positive movement along the curve. I find the best way to think of that is if you were walking into the wind on a very windy day, the wind would be working against you. It would make it harder for you to move forward, okay? Now, if the direction of the field is the same or close to the same as the orientation of the curve, then the work done will be positive. So in that scenario, we have to think of what it's like to walk with the wind. Like the wind's at your back, it's kind of pushing you along. It's helping you. So you're gonna get a positive work done. If there are places on the curve where the direction field is moving in the same direction, and other places on the curve where the direction field is moving in the opposite direction, you have to decide which one seems bigger, which one seems to have a greater value. And if it seems that there's more of the directions that are the same than the directions that are opposite, then you would expect your work to be positive. So more of the directions the same than directions opposite, you expect work to be positive. If it seems that there are more that are opposite, then you should expect the work to be to be negative, I should say. That one, that's a typo right there. That should be negative. Sorry about that. Now, if it seems like they're about equal, then you should expect your work to be either really small or 0, okay? All right, so even though we have the line integral of f dot dr is the line integral over c of f of r dotted with r prime over the magnitude of r prime ds, and the integrals with respect to arc length are unchanged when orientation is reversed, it is still true that if we calculate a line integral and we end up having to calculate it with numbers that are going in the opposite direction from the orientation of the curve, then the value that we get is actually going to be negative of what we want. So we need to pay attention to that. And the reason is because the unit tangent vector, r prime over the magnitude of r prime, is replaced by its negative when c is replaced with negative c. So the orientation of the curve still matters here. All right, now let's look at an example. We want to evaluate the line integral over c of f dot dr, where c is given by a vector function, r of t. So here we are told f of x, y, z has components x plus y squared, xz, and y plus z. So, and then we're told that our the parametrization of our curve c is given by r of t, and it has components t squared, t cubed, and minus 2t. And t is going to go from 0 to 2. So we have to come up with a few things. We need to find f of r of t, and then we also need to find r prime of t. Okay, so f of r of t, the first component is x plus y squared. So I need to go over to my r of t and find my x component. That's t squared. So I replace all x's with t squareds. My y component is t cubed, so I replace all y's with t cubed. Okay. Then for my middle component in f, I have xz. So again, the x is replaced with t squared. The z component, or the z value, gets replaced by the z component in r of t, which is minus 2t. And then my third component in f is y plus z, so I get a t cubed minus 2t. Okay. Now my r prime of t, I'm going to get directly from taking the derivative of r of t. So that has components 2t, 3t squared, and minus 2. All right, so let me just clean this up a little bit, and then I need a dot product. F of r of t is t squared plus t to the 6th. And then the second component is minus 2t cubed. And then we have t cubed minus 2t. Okay, now we've got some of the pieces that we need. We need to find f dot r prime. So that's the t squared plus t to the 6th minus 2t cubed, the t cubed minus 2t for f, dotted with r prime, which is 2t, 3t squared, and minus 2. All right, remember a dot product, you multiply like components and then add them all together. So this is equal to 2t times t squared plus t to the 6th. That was the first component multiplied by the first component. Then we have minus 2t cubed times 3t squared. Those are the second components multiplied. And then we have minus 2 times t cubed minus 2t. Those are the third components. We have to distribute and combine like terms. This gives me 2t cubed plus 2t to the 7th minus 6t to the 5th minus 2t cubed plus 4t. Those 2t cubes go away, and this finally simplifies to be 2t to the 7th minus 6t to the 5th plus 4t. This is my integrand. Okay, and then we know our differential is dt, and we have bounds already. They've given them to us. So it looks like we are set and ready to go. The line integral over c of f dot dr, just to recall it, is the line integral from a to b of f of r of t dotted with r prime of t dt. We've already calculated the thing that we need, so let's put it in. We have the integral from 0 to 2 of 2t to the 7th minus 6t to the 5th plus 4t dt. All right, so now we just go ahead and integrate. This is going to give us 2 over 8t to the 8th minus 6 over 6t to the 6th plus 4 over 2t squared from 0 to 2. I'm going to simplify my fractions and substitute my 2 in as well. So the first term becomes a 1/4, and then we have 2 to the 8th, minus 6 over 6 is 1, so I just have 2 to the 6th, plus 2 times 2 squared. And just checking my work, it looks like I have the same numbers I had when I worked it out originally. So this 2 to the 8th is going to be 256, and then we have over 4. Minus 2 to the 6th is 64, and 2 times 2 times 2 is going to be 8, and this all adds up to 8 for a final answer. So this is the value of the work. We don't know the units. It could be joules or something like that, but we don't have any of our units. Okay, so right now we would say that this is just kind of abstract. We calculated a line integral of a vector field. Okay. The next example, we are asked to use a graph of the vector field f and the curve c to guess whether the line integral of f over c is positive, negative, or 0. And then we're supposed to evaluate the line integral. So I'm going to open up CalcPlot 3D. I've got my vector function. The components are x over square root of x squared plus y squared and y over square root of x squared plus y squared. And c is a parabola. It's y equals 1 plus x squared, but only from -1, 2 to 1, 2. Okay? So I can actually draw that part real quick. I can draw c, and let's see. Two, 3, and 4. Okay, so from -1, 2 to 1, 2, and this particular line, 1 plus x squared, has a vertex at 0, 1. So we really just have this little part right here. And since we're starting at -1, 2 and going to +1, 2, I draw my arrows in that way. Okay, so c is defined by this y equals 1 plus x squared, and we could get our parametrization of this. Now y is an explicit function of x, and so that means that we should go ahead and let x be t, and then y is the function of t. It's 1 plus t squared. Now, because t and x are equivalent, the bounds for t are the same as the bounds for x. X goes from -1 to 1, we can see from the graph, So t does the same thing, goes from -1 to 1. Okay, now before I go any further with that one, I want to go ahead and pull up, let's see, here we go, Calculate 3D, and I'm going to get rid of what's on there by clearing it out. I want to put a vector field in here, and so I need components. I need x over the square root of x squared plus y squared for my first component. I need y over the square root of x squared plus y squared for my second component. And this is just a two-dimensional thing, so I don't have a third component. I just have the two. I can take this and I can restrict my view to 2D so I can see what things look like. My vectors are all scaled so that they're a quarter of the length that they normally would be. I could just half them, or I could let them have their actual length. That's a little overwhelming looking at that, so let's do halving them. Okay. The number of vectors I have along the x-axis is 9. I could bump that up to 15 and we just see more, right? And along the y-axis I could do the same, and again we just see more. So that's what's happening here. Along the z-axis, I do need 1 because that is the xy plane. Okay, now what I want to do is I want to get my, what do you call it? I want to get my graph, my space curve. Okay, so my space curve, r of t, we just found it. We're going to let x of t be t, and y of t is 1 plus t squared. And z, we don't have any z, so z is 0. And we can press enter. And I see my curve up here. On my curve right here, it's in blue. Okay, and so just let's actually get a little snip of this so we can put it in our work. And really, I only need kind of that portion of it. Okay, so going back to our work, I'm going to put this in here and shrink it down significantly. Okay, so now we have a picture of what's going on, and it looks like, let's see what's going on. So I'm seeing that we have this direction. I'm going to use a different color that stands out more. Maybe orange will be good. Oops. So here is our curve, C, and the direction that we're trying to travel. It looks like in the second quadrant, we are traveling against the vector field. But then as soon as we cross over the y-axis, it looks like the travel along the curve is with the field. So in the first side, it's against the field. And then in the first quadrant, in the second quadrant, it's against the field. In the first quadrant, it's with the field. And everything looks symmetric. So I'm going to guess that the work is 0. And then let's just see what ends up happening. Okay, so based on that, I already have my r of t, went ahead and found that so I could graph it. I need to find a few things. Remember that work is going to be the integral of f of r of t dotted with r prime of t dt. So we already have the r of t. We need r prime of t. It's going to be 1 and 2t. And then we need f of r of t, right? So f of r of t. The first component, I replace the x's with t's and the y's with 1 plus t squared. So I get t over the square root of t squared plus 1 plus t squared all squared. Second component, I replace y with 1 plus t squared. And in the bottom, I have a t squared plus a 1 plus t squared all squared. That is my vector field. And I can simplify that denominator so that I have t over, and after I square the 1 plus t squared and combine like terms, I just get the square root of t to the fourth plus 3t squared plus 1. So that's 1 plus t squared, and then over the square root of t to the fourth plus 3t squared plus 1. Okay, the next thing I need is f. I need to move my guess. It's kind of in my way. I'll put it down here. Okay, so now I need f of r of t dotted with r prime of t. So I'm going to take the first component of f and the first component of r prime and multiply them. So I just get t over the square root of t to the fourth plus 3t squared plus 1. Plus, I'm going to take my r prime, second component, and multiply it with the second component of f. So I get a 2t times 1 plus t squared all over the square root of t to the fourth plus 3t squared plus 1. Okay, now I have a common denominator already, so I can go ahead and distribute the 2t, reorganize all my terms. What I end up with is 2t cubed plus 3t in the numerator, and then I have my square root of t to the fourth plus 3t squared plus 1. So this is my integrand. We have our bounds. I found them up here. Our bounds do the same thing that x does. It goes from -1 to 1. So we're ready to go ahead and set up our integral. Okay, so if we set up our integral, we've got the line integral over c of f dot dr is equal to the integral from -1 to 1 of 2t cubed plus 3t over the square root of t to the fourth plus 3t squared plus 1 dt. At first glance, this looks impossible to do, but I'm going to try a u sub and see what ends up happening. So if I let my denominator under that square root be my u, that means u will be t to the fourth plus 3t squared plus 1, and du will be 4t cubed plus 6t dt. Notice that is almost the same as our numerator, except it's twice it. So if I divide both sides by 2, I get 1/2 du will replace 2t cubed plus 3t dt. Okay, so I have a perfect replacement right now. This is going to be the integral of 1/2 times 1 over the square root of u du. So that's 1/2 the integral u to the -1/2 du. Integrating a -1/2, we would add 1. So I get u to the 1/2. All right, so this is 1/2 u to the 1/2 divided by 1/2, which just all simplifies to u to the 1/2. Okay. So my antiderivative here is just going to be my u raised to the 1/2 power. So I'm going to get the square root of t to the fourth plus 3t squared plus 1, evaluated from -1 to 1. This gives me the square root of 1 plus 3 plus 1 minus the square root, and I'm taking a -1 now and plugging it in, but it's going to get raised to a 4th power and a square. So I get, again, 1 plus 3 plus 1. This is the square root of 5 minus the square root of 5, and that adds up to 0. So my prediction was correct. And my prediction was based on the graph, looking at the curve along the vector field and making sure to make note of the direction that I would travel along that curve. I could see that I had exactly the same amount of work against the field as I did with the field, which adds up to 0. So that's all I've got for 16.2, 3 videos worth. If you do have any questions at all, please reach out, get the help that you need, and I'll see you next time.